Okay, so I think I am live. I'm not absolutely sure, but I am pretty sure I am. Okay, I think, yep, now I am live. I'm testing YouTube. I'm going to test my audio for a second just to kind of see how everything is working. Yep, it seems that I am live. I think everything is working all right. Okay, so I'm going to have chat open on a little tab over here in Chrome. I'm going to make my face a little bit smaller. Um, Let me cut this out a little bit just so that you guys can see the screen way better. All right. There you go. Okay, so what are we doing today? Today we're going to be benchmarking Faucet. So, I'm guessing if anybody joins, you're probably already familiar with what Faucet is. If you're not, I made a little video. I've made quite a lot of changes to the program, but um, definitely, definitely, it's kind of like the same concept. So what have I done with Faucet? Mainly, I'm gonna go on Twitter. I'm gonna check if there's anything new over here. No, absolutely not. Okay, so basically, what Faucet um is, or what it's shaping up to be, because it's like such a new project. Basically, what I'm trying to make it become is some sort of load balancer for Kubernetes deployments. So it works perfectly on a local setup. It makes it. That's kind of like the thing that I showed on the video. But I got the suggestion of turning it into some sort of load balancer for Kubernetes, because many times what you see is you find kind of HTTP collisions when using like a normal service load balancer. So if you don't know a lot about Kubernetes, in Kubernetes you can have a service. So if I look at Kubernetes service, um, basically what it is an abstraction that lets you load balance across different pods. So a service is what you use when you want to have multiple replicas of the same server. The problem is, first of all, the service distributes connections randomly across the different pods. So many times, if you have endpoints that take different amount of time to respond, which is most likely the case, you're definitely gonna have collisions. What Faucet does is that it optimizes that to make it so that connections and requests are distributed in the best way possible to the different pods. So that's basically where the performance improvements are. Basically, how it runs is that you have the service, but instead of having the service distribute the different, so let me look here for headless service. So instead of having the balancer for the service distribute the connections, you have a separate service that balances those. So there's a really, I think it was this video. Yep, it was this video. So this video explains it really well. Um, Basically, I don't know if it shows it. So yeah, this is kind of like what you have here. So yeah, you have the headless service, and then you have like this would be Faucet, and Faucet would then distribute to the other pods and have the headless service so that it knows which pods to point to. I don't know if there's anyone watching. I think there isn't right now. But if anyone joins, I'm gonna be open to answering absolutely any questions that you have. Um, okay, so let's get it started. So I'm gonna show kind of like what the benchmark is about, and explain what I'm doing to test it. So I'm going into my projects, into personal, Faucet benchmark. Here it is. You also, I'm gonna put this in the description. I didn't put it in the description. This is the GitHub repo for the benchmark. So I'm gonna put it here in the description. How do I edit? Edit video. I don't want to go into the studio and reveal something that I shouldn't. This doesn't reveal anything wrong. Okay, so here, repo for the benchmark. There you go. Save. There you go. Okay. So I'm gonna go back to the repo and kind of I closed the tab. Okay, doesn't matter. Cool. So this is the repo. I'm gonna zoom in a little bit so that you guys can have a better view of the text. Basically, I have three scripts. One that is build.sh, which basically it uses Minikube because that's what I'm using on my local machine. You could probably adapt this benchmark to a different Kubernetes deployment. But I used Minikube just because it's a local environment. It works well enough for what I need. So basically, this will allow me to build the Docker images and save them directly into where Minikube stores the environment. Um, I just build the images and then I apply some rules. Pretty simple. Let's go into those images. So the one for Faucet is literally just Ubuntu Jammy, which is my operating system. I copy the binary file and I execute the binary file. I already pre-compiled Faucet, so I mean you could compile it yourself and copy it to this path, but that's on you. I just decided to send out. So if you look here, Faucet, it's okay. Faucet, no, it's a binary file. It's right there. It's just a copy. Then comes the plumber, the Docker file. Basically, what I do is here I have oh no, this is plumber. Sorry, plumber.docker file. Here it is. The other one is again just the plumber API. I'm copying the API, the folder, installing some dependencies, running ramp restore, and exposing the entry point. If we take a look at this plumber API, I'm gonna plumber.r. Basically, what I created is this stupid heavy operation function. It basically is always one, right? Because sine squared, cosine squared, and I do this iteration, whatever number I sent to it times 1,000. This is meant to kind of simulate a really heavy operation on the CPU that will take quite a long time for the server to respond back. And then I create three endpoints: stress 1, stress 2, and stress 3, that run this function many more times. So stress 1 runs this 1,000 times, stress 2 10,000 times, and stress 3 100,000 times. I still have no questions. Okay, cool. Let me see if I can go back to the video. Okay, let's continue watching. Okay, so that's basically our API. This one takes a couple, like 2 or 3, 4 seconds to run. This one takes 2 seconds, and this one takes a couple milliseconds. The thing that I'm trying to emphasize is, how would I say it? I'm trying to simulate a situation where you're gonna have different endpoints that take different amounts of time. And okay, so let's go now to the plumb mark. So plumb mark is a little program that I built. It's super simple. It takes in a couple command line arguments, and basically, where's main.rs here? Basically, I have this fetch plumber function. It's an async function. It takes in an HTTP client, a semaphore. So if you don't know what a semaphore is, basically you have to acquire a permit in order to continue running the function. This will enable me to create a little argument that allows me to tell the computer how many concurrent requests it should be sending, and the URL to which it should fetch to. It returns a duration, an amount of time. In this case, it's the amount of time that it takes to run the request. And I parse the CLI argument. I take them. I create the HTTP client. I create the semaphore with whatever concurrency argument the user sends. I create a task vector. These are the endpoints I'm gonna be fetching over and over. So stress 1, stress 2, and stress 3, which are the ones that I created. I create a start, so an instant right now, right? I iterate through the number of iterations that the user sends, so args that get iterations, and I go through every endpoint and push it to our tasks. Then I wait for all the tasks to finish, which is what this future join all does. and I collect them into these durations, which is a vector of results. Then I take in the total time that it spent doing the requests. Then here, I basically just unwrap them and sort them from least to greatest, so in ascending order. Then I calculate some small stats, so the average request time, the median request time, the 95th percentile, and the 99th percentile. I could also like add here another one, like perhaps the calculate the 25th percentile. I think would be a good stat to add. Okay, so let's just add our 25th percentile and print it right here before median. Perfect. Okay, and then after getting those stats, I print them out. That's all the plumb mark does. Okay, so now I can run ./build.sh. It's gonna build the Docker images, right? It's gonna compile plumb mark, clap, features, H2, quest, plumb mark, and it should be done. Perfect. Okay, so now I'm gonna do a little bit of clean. I should have done the clean before. On ./clean sh, I'm gonna delete the pods that already existed, and I'm gonna rerun build.sh. It's already gonna be, everything's built already, so it's just gonna create the services and the pods on Kubernetes. Hell, it's hard to believe we had two Plumber async packages within Rust. Yes. So I hadn't seen the question. Sorry. um, First of all, hi Eric, how are you? Haven't seen you in a while. So Faucet does a couple things differently. So I'm gonna go into the Valve repository because I think Valve is a great package. I spoke with a developer, and this is, let's see if I have Valve. Here is. So Valve is pretty cool. The thing is that Valve uses a pool method, like a pool architecture, and it can spawn processes. It's meant to run on a single machine, basically, and it kind of leverages the different processes, which Faucet also does, right? And here in the repo, I actually wrote a little section. What makes it different from other async runtimes? And basically, trying to focus Faucet into working more in a Kubernetes cluster. So right now, what I'm benchmarking is its performance on Kubernetes specifically. I'm guessing the performance would be similar, if not equal, to that of Valve. I don't think it would be better, but I think they will both would be pretty similar. And I think if you're gonna run on a single VM, I think Valve is probably a little bit more developed since it's a little bit more mature. But Faucet would do most of the things Valve does. That's pretty much the difference. Valve is a great project. I think it's really cool. The architecture is pretty similar. I use a lock mechanism. He uses a pull mechanism, but I think they're both pretty cool. I'm going to discuss using Plumber APIs and Shiny apps for my workshop next month. Cool. That sounds absolutely awesome. Thank you so much, Eric. So I don't know if I answered your question. Basically, in this case, Faucet is going to be a load balancer inside Kubernetes that you attach to a service to allow it to make the most performance out of your Plumber API. So I'm going to kind of show how default vanilla Kubernetes would handle those requests versus how Faucet would handle them, and showing the performance benefit on the exact same setup. Faucet versus Plumber. Perfect. Okay, so I'm going to continue right here. So now I created the services. I'm going to show the Plumber service, with which I think is the most important. So what I'm creating is a deployment with 4 different replicas. We could add or change this number later to kind of see how would it scale for more replicas. But for now, it's going to be running 4 different replicas of Plumber, right? It's going to run on port 8000, and I'm creating a headless service, and I'm creating a normal cluster IP service. The headless service is Plumber headless, and the normal is Plumber DLB. Why DLB? I just put it as default load balancer. It doesn't really matter, but they both run on port 8000. Then I create a little faucet service, and it's configured with this argument. So it's gonna run host 0.0.0. It's gonna have 4 threads to handle HTTP requests, and it's gonna use the Plumber headless as the service that it's gonna be attaching itself to. And this is gonna be it. I'm gonna limit the CPU to 500 micro CPUs, which I think is well enough for the benchmark. Okay, and I think that's about it. So now we can do /attach. We're gonna be attaching ourselves to the Plumbermark pod, and as you can see, this is just a little container. And here we can run Plumbermark. So if I write here Plumbermark, I'm gonna get kind of what I need to do. I'm gonna need to set a target, a number of iterations, and a concurrency count. So I'm gonna explain like a little bit of each of them. So the target is what are we gonna be sending the request to? To compare normal Kubernetes versus Faucet. Well, we're not Faucet by itself, but Faucet plus Kubernetes or Faucet inside Kubernetes. The target is gonna be the. Let me go back. I'm gonna deattach. To have it run on normal Kubernetes, we're just gonna point the target to Plumber DLB. And for the other one, we're going to be pointing to Faucet. Again, remember Faucet, the only thing it does is that it attaches to Plumber headless over here. And it's going to distribute the load against the 4 replicas defined here. So it's going to distribute the load in this 4 replicas with its lock mechanism. So that's all it's going to do. So I'm going to keep mbims. I'm just going to do /attach. Cool. So, are there any other questions? Not yet. Cool. So now we can just run Plumbermark, right? So Plumbermark, let's start with our target. So -t http://faucet 8080. Why? Because if we look at the faucet.yaml, our faucet is running on port 8080. This is, 8080 TCP, so faucet 8080. So the number of iterations, -i, let's say we're going to run this. Let's start with 5 iterations. And concurrency is how many concurrent requests it should be sending. So should it send 4 at a time, 1 at a time, 10 at a time, etc. So I'm going to zoom out a little bit, actually. I'm going to split my screen a little bit. And I'm going to do watch kubectl top pods so that we can look at the right. We're going to be looking at the stats of our different pods inside our Kubernetes deployment. So let's set concurrency to 4 so that it sends 4 requests at a time. That way we're maximizing the number of requests that are handled over here. So let's click enter, and it's going to start benchmarking our deployment, right? The metric server takes, 15 seconds to update, so you're probably gonna, everything is in 1 micro CPU. But as you can see now, it's distributing the load across the 4 Plumber replicas on Kubernetes. Or, well, on our service inside Kubernetes. Cool. While this is running, are there any other questions? No, there seems not to be. Okay. Let's see how this goes. Okay, so it seems to be finishing up. So this one Plumber worker is still, it has some load on it. Perhaps it's running a stress 3. So let's just wait for it to finish. This is an unrealistic benchmark, to be honest. Since, well, we're probably not going to see those kind of CPU stressful benchmarks as the one that I sent. It's on my dev wish list to become more proficient with Kubernetes. Kubernetes is not that hard once you kind of understand it. I could do some sort of series like kind of understanding Kubernetes, but it's really not that hard. So this seems Okay, this took quite a long time. Let's run it again. I don't know why it let's run it again. I don't know why that took so long. Why this plumber worker stalled. Also, I'm kind of live streaming, so let's log to my system monitor, perhaps. Yeah, I'm using quite a lot of CPU, but I think it's alright. Let's let it run again. So yeah, I could do like a little bit of a series explaining how Kubernetes works. It's not that hard. You just need to quite a lot of reading. Configuration is quite deep. You're probably gonna need to go quite. Okay, so now it ran a little bit faster. Okay, cool. So as you can see, the total time it did 15 requests. So the number of iterations times 3 because there are 3 endpoints. Total requests 15. Total time 26 seconds. The average request time was 4.9 seconds. The 25th percentile was 154 milliseconds. The median was 1.35 seconds. The 95th percentile was 13.89 seconds. And the 99th percentile, well, this is such a small data set, it's not going to do that big of a difference. Now let's run it with the normal Kubernetes setup. So let's go to 8000. And this was Plumber default load balancer, DLB. So now, as you're going to see, if we run this again, on the right, we're going to be seeing probably the same thing. It's going to start distributing the load across the different pods. But here we're using the default way Kubernetes splits the connections and the requests. We're not going to be doing absolutely any logic to kind of have different guarantees. So as you can see, for example, some of them are running a lot, some of them are running more, some of them are running like absolutely nothing, since it's absolutely random. And here, I expected a little bit better performance improvement, but it took 30 seconds against 26 seconds. So there's a 4-second benefit right there. Let's run it with some different. Let's run a concurrency of 8. Let's do 10 iterations. So let's run this to Plumber DLB to see how the default Kubernetes setup goes ahead and runs it. So right here, we're sending to the default Kubernetes service load balancer 10 iterations, which means 30 different requests, sending 8 at least, or at most 8 concurrent requests. So once they're starting to finish, it's going to be way less. So let's wait for this to finish the benchmark. From experience, this should take about 70 seconds, I think, was the last time I ran this benchmarks. Again, I'm running this on my computer. There's probably a bunch of background tasks that may make one situation better or worse. So this is not like a definitive benchmark. Okay, it took 61 seconds. Sounds good to me, sounds about right. Now let's run it with Faucet. So Faucet and send it to port 8080 instead of 8000. This is the exact same command. It's the exact same logic. We're just changing the endpoint that it's being sent to. Let's see how it does. So as you can see, the Faucet CPU cores right here increased. Why? Because we're handling more requests than there are Plumber replicas. So what that does effectively is that Faucet needs to save the requests in its kind of buffer and kind of wait for the different Plumber replicas to liberate so that it can then delegate those. So here we can see, for example, total time using the default Kubernetes setup was 61 seconds. Using Faucet, we saw an improvement. Now it's taking only 45 seconds. The average request time with the default Kubernetes setup was 13.7 seconds. With Faucet, we saw an improvement of that to 9.5 seconds. A 25th percentile was of 1.4 seconds. In the default Kubernetes setup, it was 2.7 seconds. The median was look at the median improvement. So the median request time for the default Kubernetes setup was 15 seconds. The median request time Utilizing Faucet inside Kubernetes was a 4.8 seconds. That's a big improvement. You For the 99th and 95th percentile, it didn't really change much. It was about 30 seconds. But look at the median and the average improvement. That's a really big improvement that users are definitely going to notice. I think that's like the main takeaway of this. Um, so let's run a so I I'm gonna go back to the bot and kind of write this down to kind of check out the improvement. Let's go with a little bit of a bigger concurrency setup. So let's go for what? Mm, 15 iterations. So 45 requests distributed along 16 concurrency. Yeah, let's set up 16. And let's go for Faucet first. So it's gonna do 45 iterations with at most 16 concurrent requests. Let's see how it does. I should probably do it in a little bit more of a systematic way so that I could graph them and kind of plot them into some sort of. And I should probably change the input so that I can kind of drop it into a CSV and just kind of do it super simply. But I don't know if I'm gonna take the time to do that right now. I could though. This is probably gonna take a little bit over a minute. And as you can see, like in terms of resources, Faucet only takes 3 MB of memory, which is really not a lot. Okay, so it took 1 minute, 63 seconds, and now let's run it with our like the default plumber DLV 8000. Let's see how default Kubernetes does handling those requests. It's probably gonna take like a minute and a half, perhaps even more. I have no idea. Plumber DLV. Yep, I did it correctly. I think I've been live for a little bit over half an hour now. 27 minutes. Yep. I think this is going all right. I'm probably gonna. I shared this on LinkedIn, on Twitter too. The bot is still gonna be up in case anybody wants to rewatch this for some reason. Um, and the repo is up for the benchmarks. So again, if you want to verify these benchmarks and run them yourself, you absolutely can. So this one's still running. Also, I'm not that worried about Chrome or something changing benchmarks much because I'm limiting the CPUs to .5 of a CPU for every single, so it should at most take 2 cores of my machine. So as you can see, the problem with normal Kubernetes is that it's not smart about how it distributes the different requests. For example, these two are finished. These two, they are doing absolutely nothing, and we have no idea if these. Okay, this one seemed to have finished. So yeah, look, total time 92 seconds, and total time 63 seconds. So this was a 50% improvement, right? If you're running Plumber on a Kubernetes setup, vanilla, it's gonna take for this specific scenario under a really heavy stress test, which is not probably unless it depends on what you're using your Plumber API for. I use many APIs that for short periods of time are really heavily hit it when we're like synchronizing information. This is where you're gonna see the most improvement. So look, in this case, with a normal Kubernetes setup, it took 92 seconds, but with Faucet, that's 63 seconds. I don't care if I'm running this on my computer, if there's background tasks. This is such a big margin of improvement that I don't really care. It's such a big margin of improvement that basically it makes sense for me to kind of recommend this. Um, I think everything works quite alright. Average time. Yeah, this is absolutely great. And they're the same number of requests. So the average is not that far off. I want to see where the main difference is because the median request time for the normal is 27 seconds and the median request time for Faucet is 16 seconds. But actually, the 25th percentile is lower on how do you call that on the default Kubernetes setup than on Faucet. But I don't know if this is margin of error or if perhaps there's a little bit of randomness to it. It could have been lucky, or it could have not been. Like there's just so much. That's some excellent. Yep. So when my workshop is done next, I hope to get back to live streaming Shiny. Yep, that would be absolutely awesome. I really miss your live streams, and that's an excellent time saving. So imagine you're deploying some sort of data pipeline and you're processing the information through a Plumber API. If you're gonna be, for example, doing hitting this API constantly to kind of aggregate some data, Faucet is gonna improve that apparently by about 50% in some scenarios. So I put 50% faster Plumber APIs as a kind of clickbaity way of showing it because realistically, you're probably not going to see 50% improvement in all cases, but in some cases, you might, right? So I'm kind of selling it like that. But definitely on every single scenario, there's at least a little bit of an improvement, which I think is cool, which I think is nice. I'm gonna go ahead and gonna is there what diff did I create? I added 25th percentile. Yeah, let's do it. Let's commit this. Commit feed adds 25th percentile to benchmark. Okay, just to kind of have it. So let's create a new branch. Git checkout minus b faster plumber. So what I'm gonna do is I'm gonna modify this plumber.r file, and I think it was a little bit overkill to kind of set this up. So I'm just gonna remove the times 1,000. Maybe that was a little bit because the average request time was about like 5 seconds on Faucet, which I think is still like a little bit. Let me change here, right there. There you go. Trying semicolons. There you go. Remove spaces. What's wrong with this? There you go. Okay. So I think that was perhaps a little bit overkill. So I'm gonna rebuild. So let me dot slash clean. Perfect. Now dash build. Let's rebuild the Plumber API. There you go. So it's rebuilding. It's reinstalling everything. I'm just gonna make it like a little bit of a snappier API. Just don't have those like that many iterations. And kind of test what if I run the same benchmark, but with a heavier amount of requests, but with a faster, like lighter API. And if I find this benchmark a little bit better, I'm gonna merge it back into the main. But again, this you can verify, modify, do whatever. You could replace your own API right here in the Plumber. Change the API and kind of deploy your own API and do whatever you want and benchmark if Faucet actually is creating some sort of benefit for your use case, right? But I think it is something that's really cool. Again, it's super under development. Probably it's not definitely not ready for production. But I think it's something that's definitely cool. So while this compiles, I'm gonna go to the bathroom. I will be right back. I'm gonna mute my microphone just to not have any weird noises. Oh, thank you so much. I totally forgot I was muted. Okay, so things that only happen on live streams. Okay, so I would recommend like I've used Azure, however you want to pronounce it, quite a lot. But I know a lot of people that use Google Cloud Platform, and I think Google Cloud Platform probably has some of the best Kubernetes documentation, and it's really great. Yeah, happens to the best of us, absolutely. But for personal projects, I like to use Linode. So if you look for Linode Kubernetes, it's kind of bare bones. But the good thing about it being a little bit bare bones is that you have the ability to kind of do whatever you want. Plus, it's quite cheap compared to other solutions. Yeah, I totally get you. I think I don't know. AWS also has like a really I don't like the interface a lot on AWS, but it's kind of like what we have, right? Cool. So okay, this compiled now, and now we can attach. So I want to see how plumb mark target http colon slash slash faucet 8080 iterations. Let's run what 300 iterations with a concurrency of let's send 16 requests at a time. So wait, I'm gonna copy this and I'm gonna again mvim and do term. I rather have this like this and dot slash attach paste it. So 16, there you go. Because I wanna split and watch how the nodes are getting distributed. Linode is awesome. I use them for yep. So Linode, I love Linode, the Kubernetes solution from Linode. Okay, this is done. This was quite quicker. So 900 requests were sent. It took 13 seconds. The average request time was 230 milliseconds. The 25th percentile was 103 milliseconds. The median request time was 199. 95th percentile was 594 milliseconds, and 799 for the 99th percentile. Now let's test it out with the default plumber DLB. Okay, that was quite fast. Did it? Yep. Okay, so I want to test this again. So perhaps there's something right there that I need to optimize for shorter. Yep, there's definitely a bottleneck right here when I'm running so many requests at one time. Okay, that's a new finding, something that I need to work on. But for the longer requests, there was definitely. So let's turn up this concurrency number back up to, let's say we run what, 50 requests at a time, and let's run through 1,000 iterations. Perhaps I need to turn up the CPU on the faucet container. Since it's running many more requests. Because I see there's a relatively low load on the different plumber containers. And I see there's a very high load on the faucet. So that's something that there's definitely some sort of bottleneck inside faucet. This is why faucet is not something that's production ready in any. Yeah, so I'm just gonna take my time, kind of find bottlenecks, find things that I need to work on. And as you can see, I found like a little bit of a bottleneck when I'm running many, like many requests at the same time with really low latency. There seems to be, so let's again run for 8,000 and on the plumber DLB, because I'm guessing there's going to be much less of a chance for connection collisions when you're running very quick. What do you call that? Like very quick request. Yeah. So definitely there's a bottleneck here in faucet. I'm gonna now I'm gonna go into let me go into the faucet.yaml, and I'm gonna turn the the number of CPUs that it has available to itself. Because it's kind of unfair right there for, how do you call that? For Faucet, since Kubernetes has access to my whole CPU. So I'm actually just gonna remove the limit on Faucet just to make it a little bit more comparable. Because I mean, Faucet has, like, the normal Kubernetes setup has no, how do you call that? No limit on the CPU cores that it has. So it got configured again. Let's see if, yeah. So now let's wait for the Faucet container to come back up, and let's rerun the benchmark. Let's see how it does with no performance limit. So let's attach, and let's run it on Faucet again. Is it back up? Okay, so kubectl get pods. Faucet. Okay, it's running. Watch. Okay, there it is. So let's run this. Also, I'm only running 4 workers. Probably gonna have to profile the application and test out what's, because it's still, I feel like it's CPU limited to a point. Okay. Yep, this is the normal load balancer is gonna blow it out of the water. Absolutely, yeah. Okay. So let's go back to the faucet.yaml. Let's let's set this to 16 workers and redeploy build.sh. I have a little bit of noise. You'll be right back. Okay, so there's definitely a little bit of a bottleneck. Faucet is not optimized at all. Like, the code is really messy. There's a bunch of places where improvements could be made. There you go, Faucet's back up. Let's run it again. So Plumber DVL is taking, DLB, sorry, is taking 6 seconds. Let's see what Faucet is up to. 1050. Yeah, it's definitely more than 6 seconds, but it's probably an improvement. Okay, I'm gonna have to go into the code. Yeah, it was a little bit hard at the beginning, but once you get used to it, you kind of start getting it and understanding, okay, what's up with this. So let's go into my projects, personal. Let's try to do some little optimization now that we have some benchmarks. So I'm guessing most of the time it's spending is in the locking mechanism, which is quite a hard mechanism to get right, because it's, you have to do a lot of retries. So yeah, you would have here state open. Let's look at the K8. Also, another thing that could be bottlenecking this setup is getting the socket addresses. So on every request, and I think this is probably the thing that's mostly bottlenecking it. On every request, I'm resolving a DNS. I'm going to a domain name service. In this case, the Kubernetes domain name service, but nevertheless, and I have to resolve the host name. So here, with this get socket address, um, I'm basically needing to do that. Um, so there's gotta be a way. I'm just gonna test it out to see kind of how it looks. I'm not gonna commit this, but I want to see if there's like probably someone that knows a little bit more Kubernetes could help me out. Because a headless service you kind of need to resolve in order to kind of get it working. Um, but I know with auto scaling, you're probably gonna need to refresh this because auto scaling can scale up and can scale down, and you don't want to send requests to something that doesn't exist anymore. So I don't know if there's a way to kind of get by that, or like a message, or I have no idea. Probably gonna end up creating a separate thread task that updates it every couple seconds independently of the requests that are being managed. But for now, let's do something. Okay, so um, what I'm gonna do is here, instead of doing the get socket addresses, create a I'm gonna change this method to resolve socket addresses. And I'm gonna create a new method with the same get socket addresses. Um, let's add a field to the dispatcher, and this is gonna be socket address list. So it's gonna be socket addresses, which is gonna be a vector of socket address. Perfect. And now I'm gonna let socket addresses equals socket addresses equal because okay, this uses self-set URL. Here I'm just gonna change this to URL is a reference to a URL. Let's just change this to right there. It's perfect. Okay, so now self resolve socket addresses at URL socket addresses. Perfect. And now this, the only thing it would do, instead of returning a vector, I could actually just return a slice of socket addresses that return at self socket address. Perfect. And here I would need to dereference this. I could actually just change the try acquire method to taking a reference to K. No, this requires the key. No, let's just do it like that. And let's go back to K8. And let's just dereference it. Yeah, let's just dereference this. I don't think it's going to be that big of a performance hit. Okay. So now what I changed basically is now instead of resolving the DNS on every query, we're just gonna call it at the beginning once it starts. This would have it work in such a way that Faucet would need to. Okay. Okay. So let's create a different function. Let's wrap this around our RW lock because we want to be able to write to it and change it every once in a while. So use Tokyo sync RW lock. Cool. And now here, let socket addresses read on wrap So here this would be actually await, and this would have to be an async function. Read. So now this would be socket address dot s slice. Cannot return to a local variable. Yes, of course. So this would definitely have to be some sort of vector. Unless we can have this as an arc of a slice, that could probably be socket address. And we don't have arc. Use Tokyo sync arc extended sync. Okay, there you go. So now resolve socket addresses. This would have to return arc of socket address. But no, let's keep it as a vector. Doesn't matter. I don't care. Let's just copy this. Dot clone. Yep, let's just clone it. I don't really care that much. That we will optimize later. And now here, rwlock new. Perfect. And now let's create a task that updates it. So now let's do task that updates the socket addresses of the pods back in the service every 1 second. Let's set it up. I think that's going to be good enough. Okay, so public async function, DNS task, let's call it socket address task, and this will take in self, and it's gonna do nothing in the eye. So here's gonna Tokyo spawn. So far, let's let we're gonna wrap this inside an arc. Yep. So and again, use standard sync arc. And now let's do here arc new. Perfect. And in this task, we're gonna have to clone. So let socket equal to arc clone self socket addresses. Perfect. Now we're gonna do task. So Tokyo. Give me 1 second. I'm gonna mute myself. I'm back. My lovely fiance just arrived. Okay, there seems to be no new questions. Okay, so let's continue doing. So spawn async move. We're gonna spawn an asynchronous task. And this is gonna loop over and over and over, right? But first let's create a duration. So this would be let interval equals Tokyo time interval standard, and now we're gonna do interval dot tick, right? Completes the next instant. This method's cancellation if tick is used. Yes, the branch. Yeah, so tick dot await. I'm pretty sure the first tick is 0 seconds, so it's not gonna wait to start resolving, if I'm not wrong. Yep, 0 seconds have elapsed. The first tick completes immediately. Perfect. So it's gonna tick And after ticking, it's gonna let mute socket addresses right away, and it's gonna do this. Perfect. What is wrong? There you go. Let's see. What is borrowed? Interval. There you go. Uh-huh. Mute. Perfect. Um, where is self? Okay, let URL equals self URL dot clone. Let's return here URL. Borrow here. Perfect. So everything is set up now correctly. We have our socket address task. Let's go back to main. And in this case, this is an, so now we have here plumber dispatcher. And now if let backend, no, let's do plumber dispatcher on-prem dispatcher, socket, why is it not on-prem plumber dispatcher? Oh no, this is K8, sorry. Oh, I'm stupid. So let's just set this up back to, instead of K8, let's do K8. Just decorate way to have it K8. And now let's go to dispatcher and have this to be K8. K8 and K8. Perfect. Oh, I should have just done a replace. Okay, perfect. Okay, so if this is K8 dispatcher, it's gonna dispatcher that socket away. And I don't want to await it actually. If I go back here, socket address task, back to KA, socket address task. You should just spawn the task. But I don't know if this is the best way to do it. I think this is okay. Because this, again, this really doesn't return anything. This just spawns the task. Yeah, I think that would work. Okay, let's do cargo build release. What's up with here? Into eater. Let's go back to cargo build release. K8's line 71. So get socket addresses. Back standard net socket address is not in order. What do you mean? Yes, it is. Oh, I need to await this. Of course. Dot wait. There you go. Okay, cargo build release now. Future must. Okay, absolutely yes. So, I did do it incorrectly. Thanks, Rust, for telling me that I'm doing stuff incorrectly. This should not be here. This would need to be just this. Without the spawn. Right, and now let's go back to main. And here I would need to do Tokyo spawn. So right here it is borrowed, absolutely. So we would have to take in socket addresses. How could we do this in a better way? We could set this up in such a way that it takes dispatcher, the arc of self. And here replace with dispatcher. And here with dispatcher, right? Or just self, right? Yeah, so this takes in. I would have to arc this, but I don't really want to. Yeah, it doesn't matter. We can just clone it. So we could just set it here. Because even if we clone it, it's still an arc. It's still the same objects in the dispatcher again. URL, client, the client's still the same, the dispatcher. Does dispatcher implement clone? It's an arc. Again, we could just derive clone, right? Okay, now let's go to K8. And here, derive clone, right? All of these implement clone, absolutely. And right here, we would just take self. Now can we do this without having to clone them right here? We would also not need to clone URL. Yep, so now we can just do dot clone. And now we can do dispatcher dot clone dot socket address task. Perfect. Now it should build without any warnings. Yep. Okay, let's run this. Let's see if it works. So let's go back here. Cargo build release. Cargo build release. Let's go back here. Let's open up here on a terminal. cd images faucet. Let's cp our new faucet binary. Let's run /clean.sh /build.sh. There you go. So it should have rerun the one for copy faucet. Yeah, so this one wasn't cached. Perfect. Why are there more now? Okay, let's just close this. Okay, perfect. Now that makes sense. So let's wait for faucet. Let's attach /attach, right? And let's do the same font mark. Target http://faucet 8080 qctl get pods. Faucet's running perfect. Watch. Iterations 1000, concurrency 50. Let's see. Because now it shouldn't be resolving on every single request. Did it take the exact same amount of time? Let's rerun it to kind of let it start. What that was a cold start. Hmm. Am I muted? No. Gotta take care of the kids. Yeah. Don't worry about it. See you later. Thank you so much for watching, Eric. Okay, so doing that apparently did no difference. Wow. I absolutely thought that was going to do some sort of difference. But apparently did not. Did a cargo build release? Yeah. And they copied it over. CD images, faucet, CP. Right, get diff. What's difference? Get status, modified faucet. Yeah. And even like that didn't do that big of a difference apparently. So probably the bottleneck is either in the requesting side of things or on the so it could be either on the requesting or on the locking. That's kind of like the two bottlenecks that I can see. Because of course there's gonna be some overhead. Hmm. Yeah, because if you run like 10,000 requests, Faucet is working quite a lot, but the plumber is not. But I don't know if that's got to do something with concurrency. So if I run with like less concurrency, so let's wait for this to go down. If we run like with like concurrency of 4, perhaps it's gonna be working a little bit faster. So I don't know if it's the queuing up of all those requests that is eating up so much CPU. So let's set concurrency just to 4. Yeah, so Faucet's not working that hard right there. So right now I'm using Actix Web, which is a web framework. It's not really meant to work for reverse proxies. Um, I could try writing out my own client to handle the connections, but I want to see if concurrency it's what is what's bottlenecking Faucet or what it is, because that could be what, like, as concurrency increases, how does it affect Faucet's ability to handle the loads? Okay, this is probably a little bit too big of a benchmark, so run it down to about let's run 300 requests with a concurrency of 4. Let's wait for this to reset. Let's run it. Okay, and now if we send it to the normal Plumber DLV 8000. Hmm. Yeah, this meter request time is way too low. Let's go back and let's go back to our plumber.r. Let's modify this. Let's have it take. Let's give it granular control. Let's just heavy operation. Let's just put like the number of time. I'm just gonna do some assist sleep. I think that's gonna be sys.sleep time. Well, let's just set this to millis. Let's do like some granular control. So yeah, millis over 1,000. So stress 1, I want to take 50 millis. So yeah, let's say the response time is 50 millis. Um, let's set stress 2 to 100 millis. Well, let's set it up to 75, and let's have the maximum be 100 millis of response time. I want to watch right here again. And let's just do dot slash clean. And now dot slash build. So if anyone's still on here, I don't know if anyone's still here. I'm doing just kind of testing out, looking at the ground, like how it's going. So for really, 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 really fast requests, um, and I'm kind of like also understanding what is Faucet actually good at and what it's not good at, right? So for really quick sub 10-second requests, which is unlikely, it's not. It's actually worse. It's actually way way worse than the normal Kubernetes. But now I'm creating like a little bit of a situation where I have an operation that takes 50 milliseconds, 75 milliseconds, and 100 milliseconds, and I'm gonna see. Yes, this is Kubernetes. This is exactly that. So I'm building right here. I hate how I should probably set this to always use the RSPM so that it goes up a little bit quicker, but I don't know. So what I'm doing here is creating a Plumber API with 3 different endpoints, one that takes 50 milliseconds, one that takes 75 milliseconds and one that takes 3 milliseconds. 100 milliseconds. 75, 50, 75, 100. And I'm going to be benchmarking it with Faucet. So now I know now with like precision that Faucet is worse in the current implementation when working with basically instant responses because of course like the normal load balancer doesn't have to do any logic. But I'm gonna see if for response times between 50 and 100 milliseconds if it makes sense, if it's better, if it's more performant. Yeah, I'm definitely gonna add the RSPMs to the Docker file for Plumber. Use RSPM with Renv. RSPM. RSPM PPM. Mm-hmm. Defaults to true. Yeah. So here, what would I have to do? Env. Um, this right ppm enabled equals to true. So if I run this again, will it now use the RSPM? That's the question. The ppm, sorry, not RSPM. So many of them are still being downloaded from CRAN rather than like the ppm. Ubuntu Jammy. They had a Debian finally. Cool. Okay, so now setup. This is the link that I need. Equals this. If I rebuild it, will it now force? Ah, okay, that's 10. I would have to replace this, this, and this. Right, and now we can build it. Yep. Now I should always bring it from the RSPM. Let's see if that actually works. Okay, perfect. It's actually downloading from the RSPM. Perfect. So now it's actually gonna install the. Oh no, it's installing someone from CRAN. No, I don't want it to install from CRAN. Okay, it doesn't matter. As long as it builds faster, it's okay for me. Okay, let's go back to plumber.r. So sys.sleep in seconds, right? Yep. Perfect. Okay, so now that so do ./clean and rebuild. Perfect. Now ./attach. kubectl got pods. Is everything running? Yup. Okay, let's run plumb mark. Iteration, we'll target http :// faucet 8080. Iterations 1000, concurrency 4. Yeah, so the CPU usage is probably going to be low now because we're using sys.sleep, which is not very CPU intensive. But yeah, I think 1000 is like way too much. Let's set it up to 10. Let's see how much 10 takes. Okay, 10 took about a second. Let's do 100. This should take about 10 seconds, all right? Yep. Okay. So with Faucet, 100 iterations with a concurrency of 4. Takes about 9 seconds. Now let's test it out with the normal plumber DLB 8000. Let's see if it takes longer or like where it's at. That was a little bit slower. Okay. Let's make concurrency 8 for the DLB. And let's run, let's see how it goes, how it does with concurrency 8. So it took 7 with the DLB. And with Faucet, it took 9 seconds. Okay. Let's go back to a concurrency of 4 and do 1000 requests. That would take about, let's do 500 requests. Yeah, so definitely when there's many requests coming in is where Faucet kind of falls down. Okay, that took 50 seconds. Makes sense. Let's start out with Faucet. 8080. 500 requests with 4 concurrent requests. 500, no, 1,000, 1,500 requests. How many workers am I opening up with Faucet? So Faucet YAML 16. Okay. So there's a small, it's measurable, but it's small, a small improvement. So there's definitely going to be some overhead. Um, look, this is the overhead. So if you look at the 25th percentile, it takes 99 milliseconds for Faucet, 77 milliseconds for the normal DLB, like load balancer. So there's definitely some overhead that could be corrected and should probably before we do anything else. But I think that's about enough for now. Definitely requests, like if your request takes enough time for it to for the overhead to be negligible, and the overhead seems from what I'm measuring about what 20 milliseconds of additional overhead for Faucet, which I'm gonna go and try to code up to improve. Um, if we can remove those 20 milliseconds and make them faster, which I'm gonna go ahead again and try to do. Um, I could also like get many things to kind of make the acquire methods much quicker. Well, less CPU bound, let's say, more rather than quicker. Hmm. Because they get okay. Let's see. I'm gonna get status. This is not better at all from what we measured. To get status, cargo, build release. Let's benchmark it with the default version. So let's do, did it build? Yeah. CD images Faucet. Git diff. So like git restore Faucet. Yeah. Dot slash clean. Yeah, so there seems to be about 20 milliseconds of difference between one and the other. Plum mark dot slash build sh. And those 20 milliseconds seem to be enough for um for things to change. So let's see, let's get pods. Is everything running? Yes. Let's watch. Plumb mark t http colon slash faucet 8080. Let's do 300 iterations with a concurrency of 4. That should take about 30 seconds. Yep, 27 seconds. Let's run it now with the Plum DLB. Plum ver DLB 8000. Yeah, so the normal deal, like the normal is taking a little bit longer, but there's definitely okay. 25th percentile. Yes. So there's definitely quite a lot of overhead when working with Faucet, and I'm gonna be working to get that to a lower level. Hmm. Because yeah, of course, once it receives the response, the thing that's weird, well, not weird, but not we. I definitely need to work on this 25th percentile, 77 milliseconds and 96 milliseconds. So yeah, about 20 milliseconds of overhead. Um, that's definitely something that could be reduced. But for the medium, yeah, even for the medium, there's about 20 milliseconds. Once we get to the 95th percentile, um, it there's definitely an improvement using Faucet. And then for the 99th percentile, so like the slowest ones, there's a really really big improvement in performance. Okay, that sounds good. So for now, my conclusion is if your API um, has requests that were 20 milliseconds, um, how would you say it? Like, where the overhead of using normal Kubernetes is greater than 20 milliseconds, it seems like Faucet will give you a benefit. If not, it probably will not. So for requests that are like under 1 millisecond, under 20 like under 40 milliseconds, under 50 milliseconds, I think the improvement's not gonna be that big. The improvement for most people is probably gonna be really really low, but for other scenarios, it could be beneficial. Especially look at this 99th and 95th percentile. It's so much closer on Faucet because it knows how to distribute this. I'm gonna try to get this, um, like the difference in the lower percentiles to be lower. I try to get that working a little bit better because this is still quite a long time that we could like improve on. 20 milliseconds times 300. That's about 6 seconds that we could shave off. Yeah, if we extrapolate this to something where I'm gonna have to graph this probably, kind of get this benchmark into a CSV file so that we could like test things out and kind of graph them out. But I'm gonna try to do some optimization and